Hello everybody, and welcome to exercise 3 on page 51 of the workbook. Let's take a minute to read this question together. So we've got a thick rope of length 30 meters hanging over the edge of a tall building. During the night it rains, and after the rain is over, gravity causes the water in the rope to gradually sink, resulting in a rope that's heavier at the bottom than at the top. And specifically, they tell us that the density of the wet rope at a distance of y meters from the top of the rope is given by the function rho of y equals 1 plus 0.03 y kilograms per meter. Okay, and given all that information, we want to figure out how much work it takes to lift the wet rope to the top of the building. All right, so let's start with just a little diagram here. Okay, and let me see, I'm going to maybe give myself a little bit more space here. So here's our building, and you can imagine the rope maybe just hanging down the side of the building like this. Okay, one thing that they tell us is how long that rope is. Okay, 30 meters, so I'll go ahead and draw that into the picture here. And we're going to use the same strategy that we've been using for these types of problems. We know that different slices of the rope are going to have to move different distances, so we'll use a slice-by-slice approach. Maybe think of our slice as being there and moving a distance of y to get to the top. Okay, so there's our slice. Okay, and this problem, the setup, is going to be similar to all the other problems of this type that we did. We're going to start by just seeing, can we figure out what the weight of just that one slice of the rope is? Okay, so the slice weight. And it's going to break up into the three components that we've been breaking it down into: the density times the length times the acceleration of gravity. Okay, if we just do a quick units check on that, our density, we can see the units on that is kilograms per meter. Length is going to be measured in meters, and gravity is going to be measured in meters per second squared. If we do unit cancellation, we can see we wind up with kilogram meters per second squared. That's newtons, which is what we want. Okay, now there's one other kind of interesting feature to this problem, and that is that the density is not constant in this case. They're telling us that the rope is heavier at the bottom than it is at the top. And so instead of having a number for the density, we've got a function. It depends on the value of y, where we are in the rope. That's okay though. It just means that we're going to have an expression instead of just a constant for that density. Okay, the length of the rope, as we've been calling it, is just dy. It's a really thin slice, and then the acceleration of gravity is 9.8. Okay. And we could do a little simplifying here. So we could take this 9.8 maybe and distribute it through those two terms. I'm going to put the dy on the end. So if you take 9.8 and distribute it through, you're going to get 9.8 plus, and then you'll take 0.03 times 9.8. That's going to give you, let's see, what is that going to give us? I believe 0.294 y. Okay, that's just a little bit more simplified of a way of writing this expression. And our units, as we talked about above, should be newtons here. Okay, so that's the weight of the slice. What is the distance that it travels? Okay, well, we can see from the picture that the distance traveled, looking at the picture, is y meters. Okay, and so to get the total work here then, we're going to start with the force times the distance of just our one slice, and then we're going to add up all of the works by taking the integral of that. Okay, so it's that typical one slice at a time approach to finding work here. So let's see, we've got that, we've got our y and dy. And then lastly, what would the limits of integration be here? Okay, so as you move, kind of looking at our picture over here, from the top of the rope to the bottom, what is the range of distances that those slices might have to move? Well, the very top slice just has to move 0, and the very bottom slice of the rope has to move the entire 30 meters. Okay, so we should be getting 0 to 30 for our limits. Okay, and the rest is calculating this integral. So let's see, we might start by taking this y and just distributing it through. Make this integral easier to do. So we're going to get 9.8y plus 0.294y squared. Okay, we're ready to take antiderivatives. So let's see, that's going to give us 9.8y squared over 2 plus 0.294y cubed over 3. And we need to evaluate between 30 and 0. Okay, last step is to plug in our limits. So we'll get 9.8 times 30 squared over 2 plus 0.294 times 30 cubed. Okay, and that's our upper limit. And if you substitute 0 in for the lower limit, you're just going to get 0 for everything. Okay, and so the upshot of it is, we'll just take those numbers, substitute into our calculator, and here's what we should wind up with, it looks like. Okay, 7,056 joules. Okay, that should be our final answer.